Thank you, everyone who has joined us for today's webinar. I'm very excited for today's topic. We're going to be tackling the $2.41 trillion problem, code reliability, code quality. And what we're going to be doing is analyzing some data that Sonar has done, has researched on to figure out what are the top issues that occur, top bugs that our software finds in order to help customers better understand the quality of their code. I'm Anirban Chatterjee. I do product marketing here at Sonar. Joining me today is Tom Howlett, who runs product management. If we move to the next slide here, I do want to cover a few housekeeping items. First of all, as you may already be aware, this is a 45-minute event. We will include a Q&A at the end for those of you who are asking questions. There is a chat Q&A box that is available to you to put questions in. We don't have live question answer in this event, but you can type your questions to us in the Q&A box, and we will see them, and I will try to ask those questions live on air as they come in, and then Tom and I will do our best to answer them. You will also receive a follow-up after this event concludes. Look for an email in a couple of days after today with a link to the recording. You are obviously welcome to share that with any of your colleagues who may have missed our event today. You will also get a survey after the event, and we absolutely welcome any and all feedback you have on what you liked, what we can improve for next time, and any suggestions for future topics you'd like to see us cover. We've been doing these events with the Sonar community for years now, and we really enjoy the opportunity to have a dialogue with you guys. So if you have any suggestions on what we can do in the future, please send those in that survey that you'll see. Next slide, please. So as I mentioned, I do product marketing here. I've been here for about a year. I've been involved in IT and software for about 20 years. So I have a little bit of a background, but not nearly as much as our featured guest today, Tom Howlett, who is the head of product management at Sonar and leads the code quality domain. He's been building software for startups since the 90s and has a very deep bench of knowledge when it comes to how to write high quality code. And I'm really excited to learn some things from him as we go through the event today. Tom, welcome.
Thank you.
Let's quickly cover what we're going to talk about today. As I mentioned, the cost of poor software quality is very high, and we're going to put some numbers to that today and some analysis that we've done. I'll introduce you to the State of Code reports that Sonar has released over the past 4 weeks. I think all 4 of our reports are live now on our website, and we'll talk about that. Following that, we'll talk about the 5 most common software bugs that our software found during the analysis period that we explored, along with the most common blocker bug that SonarQube uncovered. Finally, we'll touch a bit on code security, since I know that is a hot topic for you guys. Next slide. I do want to start the conversation with this, and this is something that has come up numerous times, both in our market observations and in our one-on-one conversations with our users and customers. And that is something that our marketing team calls the engineering productivity paradox. I just call it the gap. And the gap is between the volume of code that is being created today, largely because of the rapid adoption of AI tools, and the still limited amount of bandwidth that engineers have to review that code and verify its security, reliability, and maintainability. And so the gap between those two things is growing at a fairly exponential rate, and it is something that is going to impact software quality soon if it isn't already. And it is something that Sonar is paying very close attention to, because our customers are running into this problem where they have this high volume of code. They do not have this, the bandwidth to review that code. And so as a result, quality issues are slipping through. And so because AI code is learning from developer-written code that's been written, for years and years in the past, it is mimicking a lot of the same common problems that occur even in developer-written code. So the code that SonarQube analyzes includes all of this, obviously. And so we are able to see some of the top issues that result. If we move to the next slide, not fixing these issues can have real consequences. And the temptation when you see a gap that is widening and widening and widening over time, the temptation is to take shortcuts and try to close that gap. But that can have a real impact, right? And you'll see on here that we see, over $4 trillion that is attributed to costs of data breaches in 2022, $2.4 trillion associated with poor software, and $85 billion per year GDP loss from development time that is just wasted on dealing with bad code, poor quality code, code that isn't maintainable, code that has bugs in it, code that was refactored poorly, and so on, right? All of this adds up to a lot of cost that drags software engineering. And so we exist kind of to help you guys reduce that cost. Next slide. The way we do that, as many of you know, is with the SonarQube portfolio of solutions, which helps developers improve code quality and code security from the very beginning of the development process. We're not bolt-on tools. We are part of the developer workflow. We're in the IDE, and we help developers find and fix issues very much at the front end of the process. If you click one more forward, Tom, we're going to be focusing primarily on code quality today, which I know is very near and dear to your heart, Tom, since you lead that group at Sonar. We analyze code quality across over 35 languages. We provide real-time feedback in the IDE across them. And we have dashboards in the product that show overall code quality in your code base. And we catch about 76 issues, and these issues span reliability, security, and maintainability per developer per month on average. That's what our research showed. Before we get into the specifics of the issues, we do have, actually, no, next slide, please. We're not there yet. This is the state of code series of reports that we've been working on. We took data from the analysis that SonarQube ran over a 6-month period last year, so from July to December of last year, and we analyzed that code to find the top issues in each category of issue that we explore. We have 3 quality criteria that we look at. We look at reliability, security, and maintainability. Reliability is basically software bugs. Security is things like vulnerabilities and hotspots, and maintainability primarily refers to code smells. And so we have reports on all 3 of those. We also have a report that we just launched earlier this week that is a look at all 3 of those things across specific languages. So our report includes a data set that captured data from 3 languages: C++, C#, PHP, Python, Java, JavaScript, and TypeScript. And so we have sections in that report for each one of those languages, along with the top issues for each. And so you can find all 4 of these reports on the website on your screen. We will be primarily focused on, if you advance one more, the reliability report and the top bugs that we find that impact code reliability. Next slide. So just a little more detail on the data set that we explored. As I mentioned, those 7 languages from a period of 6 months last year. That data set ended up at 7.9 billion lines of code that was analyzed across nearly 1 million developers, 970,000 developers across 40,000 organizations. And in the aggregate, our software uncovered 445 million code issues across all 3 categories: reliability, maintainability, and security. And those are spread across about 5,300 unique quality and security issues. But on the next slide, as Tom briefly showed, we have a quiz for you guys, right? Just to make sure that you guys are all paying attention. I want to see what you all predict as the number of reliability issues, reliability bugs, SonarQube saw per million lines of code. So go ahead and use the window on your screen that just popped up to give us your guess. Is it 510? Is it 1,200? Is it 2,100? Is it 10,500? So we'll let this poll go for about a minute or so. Looks like 2/3 of you have chimed in so far. Gonna wait for a few stragglers and then we'll continue. Okay, so it looks like well over half of you are pretty pessimistic. You think the answer is 10,500. About 10% of you think it's 1,200. Almost nobody thinks it's 510. The correct answer, and I'll have this on a slide later, is 2,100. So about a third of you got the right answer there. Let's go to the next question. Very similar question about how many bugs did SonarQube see per developer per month? Give it a few more moments. About two-thirds of you responded so far. Okay, so about a third of you think it's 42. A little under half think it's 11, and a quarter of you think it's 3, which, if we'll go to the next slide here, is the right answer. It's 3. So a pretty pessimistic crowd today. You're actually, developers are actually better than y'all think. 2,100 reliability issues were found per million lines of code analyzed by Sonar, and about 3 per developer per month. So we thought that was pretty interesting. I was also a little bit surprised that the numbers were this low. I think we all sort of expected them to be a bit higher than this. I will say that it only really takes one to ruin your day. So the fact that it's this low is encouraging, but we obviously want to focus on making sure that our code is as bug-free as possible. And that is what Tom is going to be talking to us about. So Tom, I'm going to throw it over to you.
Cool. Thank you, Annabelle. I think part of that reasoning as well is that they're the bugs that get to us, which hopefully other people have good code review processes and spotting them during their processes as well. And actually bugs are a relatively small proportion of our overall types of issues that we find. So, well, compared to maintainability issues, there's certainly more. So yeah, um, today I'm going to go into the 5 most common bugs, as Annabelle said. Um, what I've done is I've kind of looked through one of our test systems. So when we're developing analyzers, the developers do a lot of different tests. So there's obviously unit tests, integration tests. They make sure they capture all the different cases. But one thing they do is they deploy this to this big system we've got that's got 500 million lines of code in, and um, and I think there's how many projects? 2,000 projects on it, and they just go and look and kind of basically search through and see what it's picking up, what it isn't picking up, kind of thing. And so I've kind of delved into that system today, and it's a big searchable. It's a data center version, so you can kind of search across the board for certain types of issues, and we found some today. So yeah, one of the other things we do when we're developing the analyzers is if you guys are using SonarQube today, one of the options you'll see when you see an issue is to mark it. And you could mark it as potentially saying, this is a false positive. So occasionally you might spot something that's a false positive. And we actually have a tool that basically brings that data back into developer IDEs so they can see when some of the rules that they're creating are being marked as false positives, and they can get fixes out really quickly when we do. So just a note on that, if you're a developer using SonarQube and you're marking things as false positive, we do take note, and we do try and do something about it as quickly as possible. And obviously not all of them get fixed straight away because they can be quite complex, and we can kind of dig into that a little bit later. But anyway, let's get on and we'll go into our 5th most common bug, and which is, oh my gosh, here we go. So conditionally executed code should be reachable. Um, and so this is really another kind of name for dead code. I'm sure you've all seen it if you're a developer, code that is there in the code but actually never gets run. And we kind of do data flow analysis and we check all the paths and we can see when data isn't run. And so there's a good example of that here. I think this is C sharp. I've kind of picked different languages and different open source projects. These are all open source projects these are from, so nobody's private code. And we can see here that somebody's put a ternary check in, which is quite a common thing where you're kind of checking that there's some chapters, and if there is chapters, we'll do something with it, and if there's not chapters, we're going to return null. And that seems like that's a really common pattern we see a lot. However, if we go a bit further up the code, and I haven't included the cold code here, you could see that it's actually unnecessary because somebody prior to that is checking that chapters count is less than three. If it's less than three, it would return. So it would never get to that point. And our data flow analysis can follow the paths through and see that that happens. And you can see that's quite a difficult thing for a developer always to spot. But in reality, there's code in there that isn't being used. I mean, this is kind of there's two real reasons. I mean, in this case, it's kind of an unnecessary defense. The developer's being defensive, which isn't a bad thing, right? Perhaps overly defensive here, and done a double check. And that's not a big problem. But sometimes it's a logic error. Sometimes it's the developer not really understanding what's going on. And that might be the case here because maybe they'd forgotten about this count of three and not going in, and they're writing more code around kind of the possibility that it's two or one and things like that. So so often it's a logic error, and it's kind of really good to spot these and remove this and clean the code up as much as possible. I think one of the other big impacts of issues like this is the developers spend a lot of time trying to work things out. Why is that bit of code there? Was it supposed to be there? Was it were people am I missing something? Do I understand it? And I think a lot of developer time, and I remember as my days as a developer, was spent trying to work out other people's code and why the hell it looks like this. And so it's kind of a maintainability as well as being a reliability issue here. Um, so yeah, this is another one. I mean, this is a kind of a this is an interesting one where somebody's created a list, and then said, if the list has got more than one item in, I'm going to write out to a log, right? I guess this is some sort of writer that's serializing some object. However, there's no code in there that actually adds anything to the list. And so our data flow analysis can spot that and see, okay, nothing was ever added to the list. This is never going to get called. And actually, when you look a bit closer, when I read this code, I see, oh, actually, there's a to do. So one of those classic developers like didn't quite finish the job, left a to do in there, and the to do never got done. That's probably years old, and this bit of code is never getting run. So it's another case where this is really a kind of a requirements issue. The thing was never completed as intended.
This is super interesting. But one thing that came up, this takes me back to when we wrote the first report on reliability that came out maybe 4 weeks ago. I was doing some internal review and I was getting questions on like, hey, is this reachable code thing a real issue that we should be highlighting? It seems like it's not hurting anybody. And I think you're making a very strong case for the fact that oftentimes it could indicate a logic error,
Mm,
something that someone thought they were going to execute but forgot to execute, or thought they were going to write but then forgot to write, or another developer downstream has to now come in and make sense of the code, and now they're wondering if something should have been done that hadn't been done. But I imagine there's also occasionally cases where like a developer knows that they need to do something. They're putting the scaffolding in now and they plan to fill it in later, but it's not necessary now. And so false positives could potentially occur just due to that. And I'm curious, like how do we do what's our philosophy on false positives? This is actually a question that sort of was coming in on the side. I thought it was
mm.
good opportunity to bring it up now. Do we have a philosophy on how we decide to flag or not flag things in order to avoid false positives?
So, so yeah, it's a really good question, and it's a good one for issues like this. But when we're getting into data flow analysis, it is really difficult to calculate everything that's going onto the code. It's hugely complex, and there is only so much you can do with static analysis. Static analysis isn't a perfect science. We can't detect everything correctly, and we make certain assumptions, and there's certain things that we don't necessarily handle and don't necessarily spot. So occasionally, in issues like this, there are false positives. For an issue like this, I mean, I kind of lead the domain, and for issues like this, we try and keep them below 5% reported false positives. So mostly, hopefully, 95% of them are good, and I think that's a kind of trade-off that most developers are happy to take. And we kind of optimize around that, right? So if we're kind of making a change to the rule that's fine, detecting more, but there's more false positives, and we're going above something like that 5%, we'll change the threshold for different rules depending on how critical they are. We'll then go and do some more optimizations and improve the false positive and invest more time in that. But it's always a little bit of a trade-off. And that's why it's really good when people report false positives to us, because then we can see that actually this probably situations that we haven't covered in our scenarios that we're not spotting that we can often add in. And we basically create new test cases for those false positives when they're reported and then fix them effectively. So So yeah, it's not an exact science, especially for complex rules like this. You can imagine how hard it is to write code to detect, follow this flow, to check what type it was, to check
Yeah.
what values would have caused the if statement to go here or there. And so yeah, some rules are super simple and they're like 99.9% always right. And some rules like this, they're not so. And you get things like metaprogramming and things like that that really mess us up. And that's those are areas where we will back away.
I imagine those optimizations happen automatically if you're on the cloud product, but if you're in server, do you need to do you get those updates when you update the point release on server? Is that how to
So,
get them?
so yeah, exactly. You get a new set of analyzers. I mean, in most versions, there's a new analyzer for each language. Well, all of the major languages. So certainly these languages we're looking at today in each version. But on cloud, basically, as soon as the analyzer has finished it, we finish the testing on the analyzer, and we've all done the validation our end. The actual analyzer developer can commit it, and it will get deployed onto cloud through continuous deployment. So you get the latest and the greatest on cloud.
Awesome. Thank you. And thank you to the audience member who asked the question.
Cool. Okay. I'm actually going to hold on. So this is no. Let's keep going. I've got one more. Actually, got one more example of this. Hold on, let me jump through. So I'm going to actually jump into this is actually Sony Cube Server. This is the latest version. In fact, it was updated today to 10 point. I'm sorry, 2025.4, which I think is about to get released as a full release. We did the technical
Coming
release
soon, yeah.
Monday. Um, and so here we can see another one. This one's Python. Yeah, Python. And it's got some really sort of classic idiomatic Python, which I kind of love, which says return this if this is true, which is it's kind of unusual in most languages to have it that way around. And often it's kind of hard to actually spot the flow. And you can see on the side here, we've got the execution flow. So SonyCube will pick out the flow to help the developer understand the path that is leading to this problem. And in this case, we can quite easily see that it's testing on API user, and weirdly, API user is always false. So it's never gonna return that there. And so that's a fairly simple one, but just really to show that we do the data flow to help developers understand these problems because they can be really hard. It's really difficult if you get this is most linters you'll see it. This is a problem, but it won't tell you like how to kind of diagnose the actual things. Cool. All right. I'm going to go to number 4. I think we've spent enough on conditionally executed code. And the next one is actually an accessibility issue. So mouse events should have corresponding keyboard events. Obviously, this is a great thing if you're not able to use a mouse, and it's actually potentially a reliability issue there. You cannot use the product if you're unable to use a mouse, but it's actually a good accessibility feature for everybody. Everybody can start. People that love to use the keyboard, including lots of coders, don't like to use a mouse, can kind of use things here. You might argue that this isn't actually a reliability issue, that it's more of an accessibility issue. And actually, this is something we're considering in future versions of the product to have an accessibility categorization for qualities and potentially for other kind of areas like this where it's kind of difficult to categorize into one of those three at the moment. So yeah, this one obviously it's got the lots of mouse events going on, but nobody's put a keyboard event. And for years, people have kind of ignored this, but we've now, if you're developing or application is running in Europe, the European Accessibility Act is now in place and is enforcing this. So that's mostly based on WCAG 2.1, of which this is one of the rules. So there's a real reason now, from a compliance basis, as well as doing the right thing for your users, to make sure that you're kind of conforming to these standards. And in fact, we're going to develop more of these accessibility rules. We've got that planned and some reporting around that hopefully coming soon. So yeah, this is one area we really cover. I'm just going to jump across to an example of this one so we can have a little bit of fun with it. So oops, let me go up to here. Okay, yeah, so this is another example on TypeScript. And in fact, when you see the issue, you can also look into why is this an issue, and we'll give how to fix it. And here it's got an example showing for the framework or not the framework there. But we also have this feature AI code fix, which has been introduced recently. in fact, it's been alpha for a while and is about to go GA, I think, anytime. And so here we can actually generate a fix. And so I'll click generate. Now I do have a rule with demos that I'll never demo with animals and AI because both are unpredictable. And so hopefully this one's going to work, and it looks like it has. So you can see it's kind of it's done a diff, and it has basically added the on key press with it's actually selected it around the enter, and it will open just like the mouse click will open. So you've got a nice thing added there, and that was done fairly easy. So we have AI code fix on quite a few of the rules, not all of the rules at the moment, and we're continuing to grow that. But it can really help developers, understand how to fix it, and it uses the guidelines that we state on how to fix something. So it's not just coming up with a random fix, and it's generally fairly deterministic. It's not always the same, but it's for AI, it's reasonably deterministic. Right. I think that's everything on that one. Sorry, I'm jumping about a bit here. Yeah, okay. Let's move to the next one. So we're well on in time. Okay, floating point numbers. I'm sure I don't know if we've got all developers on or the different people, but you're probably aware of floating point numbers, which are really an approximation of a decimal number. The way they're represented in binary isn't perfect, and so arithmetic with them can cause unpredictable results. There's an IEEE 754 standard, which kind of explains how it works, and so it should work consistently. However, implementations of this standard do vary depending on processes and runtime environments. So you're still kind of taking a risk. So we look at these asserts in a test today, and we can see that this test might be running reliably today. You might change processes and move it onto a different machine or something, and the standard isn't quite implemented perfectly, and suddenly that will be actually evaluating to 18.78.00000001, and the test will fail. So I'll jump and do another example here. I'll show another example. And we've got this one, quality test. So this one is testing against two variables, again in a test. Let's generate the fix, because that's a nice example of how we fix this issue. Okay, in fact, it's gone and fixed multiple issues on this file. And you can see it's done, and basically it does what's effectively what do we call this? We call this it's basically an approximation of the thing. So I forget the technical terms here, but yeah, there's some good descriptions around this, and we can see how that's working nicely there. Yeah, so hopefully that would save somebody's test becoming brittle one day when they deploy it to a different server.
This is a good example of an issue that might work great for,
Yeah,
5, 10 years, right?
yeah, yeah.
And then at some point, someone moves to a new processor, or they switch to a new compiler, and then it breaks, and it takes forever to figure out why, because it's a part of code that no one's touched, and the person who wrote it left the company a long time ago or something. So this kind of
Exactly.
thing can be really pernicious.
Yeah, it really is. Yeah, yeah, yeah. It'll work every day until one day, and then it'll be very hard to spot why. Um, yeah. Okay. Okay. All right. I think that'll do for that one. I'm mindful of time. Right. So you can probably guess what number two is based on this quote. Um, so I don't know if I'm sure anyone that's a developer is well aware of the challenges of nulls and how much pain they can cause. I think I'm still having nightmares about nulls from my days as a developer. And this is a quote from Tony Hoare, who developed one of the early object-oriented languages, and he kind of claims that almost by accident he allowed null references, and when they designed the language, it was every reference was going to be checked, and it was easy to implement putting nulls in. So he kind of did it, and he suggests this could be it could have caused $1 billion of pain and damage. I think based on my estimation, the amount of times I spent fixing nulls as a developer, it's probably a fair share of the numbers that we showed up here. So I suspect it's a lot more than $1 billion of damage being done by this. I imagine somebody else would have done it if he hadn't anyway. But so yeah, so you'll probably guess that our next one is, as we describe it, as null pointers should not be dereferenced, which is a kind of technical term to say don't call methods on nulls, or don't call things on things that could be null. Um, it's super hard, and I'm sure it just tends to churn up a null reference detection, and it's really hard to know where the null has come from. It's really hard to work out how the thing became null. So it takes a long while to debug. It only happens under certain circumstances. So you could have a good set of test coverage. You could cover almost all of the paths, but not one path. And and that will be the one that occasionally causes a null in your live environment, throws an error message to everybody. That could potentially reveal some sensitive information. And so yeah, these are probably the most painful, I would say, even though they're number two. Let's have a look at some cases. So I'll jump into, let's do this one. Uh, okay, uh, here we go. So again, this is one that hard to work out. So we can see here that so fix this the access on a value that can be null, and it looks like method can be null. It's calling two different, or three, oh, a whole chain, a whole huge chain on method. Um, and then if we go up, we can see that method was declared here. And yep, that's obviously nullable, I think. And then below it checks to see if method is not null. So the developer is obviously aware that method might be null. And then in the next branch, it checks that bean should not be null. However, it then calls for a method. So it missed out the check for method being null. I haven't considered that case here. So I think that's a classic issue. And you can always see what's happened there, right? He's kind of focused on bean on this one and focused on method on that one, but then happened to call method on this one. I think it's kind of fun looking at these issues. You can almost tell what was going through the developer's head when they did it. Okay. And
So there's
probably,
another question that's come in that I'll ask you about now since it might be relevant. For
mm,
these rules, I know there's some cases where we have rules that exist in Community Edition and some that only exist in paid editions.
mm,
And I think for this one, there might be a nuance that would be relevant. Like,
yeah.
can you talk about that a little bit?
So, so finding nulls is probably the hardest thing we do in static analysis. And we have an advanced bug detection squad. Well, on my team, there's an advanced bug detection squad, and this is probably the thing when they're developing their analyzers, is the thing they focus on first. And the methods they use work for other things as well, like concurrency issues and things like that. But nulls is kind of where they focus. And if we do a good job on that, we've got the technology to do a good job on other things. We've recently developed a new analyzer that's working on this null detection rule in Java, but that's only available in commercial editions. And on the community edition, there's still null checking, but it falls back to a less a analyzer that's open source and less good at detecting all of the nulls. So we don't capture all of these by anything, but it would just take too much analysis. Your analyzers would run for too long. But the new one is much more efficient and able to catch a lot more of these than we used to in the past. And we've seen that since deploying it. We're seeing the numbers go up on the number we're detecting.
Awesome, thank you.
Cool. All right. I think that will probably do for nulls because we're shooting through time. Let's go to number one. Oh no, I've got here, sorry. Back to my slides. So number one is a bit like number five. Which is sort of another example of kind of dead code. So non-empty statements should change control flow or have at least one side effect. And what this kind of means is sometimes people write code that does absolutely nothing, and the code is passed through, but it has no effect whatsoever. You could take the code out, and it would make no difference. This again is similar to number five, where it might just be redundancy, but it's often a logic error. And there's this classic one here where I guess somebody was assigning result as zero, but actually put the double equals to check it was zero, or was it, right? And then again, as a developer, you've got to kind of work out what was the intent here. And so yeah, so let's have a look. I think I've got another one here, and actually, yeah, this is an interesting one. I kind of when I looked at this it took me a while to kind of work out what's going on. In fact, let's go and have a look at it. I think it's this one. Yeah, here we go. Here it is in SonyCube. So I said, if okay, diagnostic errors, but it doesn't do anything with diagnostic errors. And I spent a lot of time thinking about this. And then below it does some checks on diagnostic errors. And then I'm kind of come to the conclusion that the developer was using this as a debug. He would put a breakpoint just here, and then he would look at diagnostic errors to see when he was developing the code, which is kind of fine, but it's redundant and it's kind of confusing. And you're kind of wondering when you look at it, what were they trying to do with diagnostic errors at this point? So again, it's kind of one of those bugs that's may well be a logic error, but is kind of confusing. It's always fun to try and generate the AI fix. So let's see what AI does with this one. And I'm guessing, okay, so it said, well, let's console error the diagnostic errors, which is probably a logical thing to do, but maybe not what the developer intended in this case. Okay. Right. And so that's our five. And now we'll go to our biggest blocker. So we don't get quite as many of these, but a blocker is our highest severity. So um, obviously probably be stopping somebody's quality gate. You are likely to put a bug in. And its resources should be closed. I'm sure there's nothing worse than if there's one thing worse than a bug that throws an error, it's a bug that slowly destroys your application architecture by consuming all the memory, and everything starts slowing down and everyone's panicking what's going on, and often it's something like this, or alternatively it starts locking files, right? And suddenly, yeah, why is this file locked and why can't I access this anymore? And it's so hard to work out what locked the file, where did that come from? So I think this one is, for me, it's a blocker, not necessarily, well, kind of because of the impact, but also they're a real pain to work out what caused this resource being consuming memory or blocking
Pretty sure
things.
my browser has a few of these that they're still working on,
Yeah,
honestly.
yeah. So yeah, and let me jump through. So yeah, there's some nice ways. I mean, in the past, people would catch this with a try catch finally and make sure in finally that they would close the resources. Most languages today have this kind of block syntax. So try with resources is the Java version. I think there's a version in most languages now where you kind of open the resource in a block, and then once you leave the block, it's guaranteed to be cleared up, which is a nice way to go about it. And so, yeah, we recommend using that when you're using a modern version of a language. Yeah, here's an example. It's a sort of a bit of a classic one, really. So somebody's created a directory. In fact, let me jump onto this one on the actual site. It's easier to see. Oops, here we go. Here we go. This is the one. So yeah, it's opened a directory. And at any point, if there's an error on any of these going on, then that directory is not going to get closed. It will stay open. And there it says use resources or fine with a thing. Okay. All right. I'll jump back. So I think that is my lot. Um, cool. Anaban, I think we're back to you. If there's any more questions.
Thank you. Yeah, so we're nearly at the end here. I just wanted to quickly plug if you enjoyed this look at software bugs that are software finds, that SonarQube finds. We have another one of these webinars planned in September where we're going to focus exclusively on security issues. And this is going to include software vulnerabilities as well as security hotspots. And we're really excited to do a very similar exploration. We're also going to be talking about secrets that we uncover because we also have secrets detection in our platform. And so we'll also talk about the top secrets that are often hard-coded into the software that we analyze. So if you'd like to come back and join us for a security spin on this topic, come look for an invite on September 17th. We won't have it on our website for a little while because this month, actually in August, we have another topic teed up. If you go to the next slide here, and this actually goes directly to a question we got from the audience about CodeFix. Tom, as you were demoing CodeFix, a question came in asking if it's available across the board. I know there was an alpha/beta program that limited the availability, not just in the rules that it covers, but also the products that it's in. It is actually generally available now. It is available in server and cloud today, I believe. And we actually have a blog on
Yeah.
our website that announces this. And on August 27th, so about a month from now, we're going to do a webinar specifically on AI code fix just to show you guys how it works, where it can be used. And Prasenjit on my team, as well as Alexander on your team, Tom, will be running that webinar at the end of August. So we're looking forward to that. I think that is it. for us. As I mentioned before, you will get an email with the survey, as well as a link to the slides and a link to go download the reports and read them yourself, because we have reports on reliability, security, maintainability, and a languages report for the 7 languages. So if you want to do some more reading on any of these, the security report in particular, before our security webinar, please hit up our website and get those reports to do that. Share them with your colleagues and send us any feedback that you have on these reports and how to make them better next time we do them. That is it from me. Tom, thank you very much for this look at code reliability. I learned a few things. I hope the audience did too. And we will see you all next time.
Cool. Thank you. Thank you, everyone.